Okay, so let's get started. So today I want to do the chapter 7 exercises. Then after that, I want to go to chapter 8, the regression trees. Yeah. And before that, the last quiz, the March 24th, number 2, even if you submitted on time, it sounds it's marked as late. So I don't deduct any points. So don't worry about it. Probably that's a glitch. And today I want to do the exercise 9, that is the regression, the splines. So splines are useful, especially when you want to fit some curve on your complicated relationship between X and Y. Yeah. Okay, so we do exercise 9. So maybe I do the first few preliminary steps. Then after that, I would like you to discuss with your classmates. So exercise 9 is already available on the website. So I will show the exercises. So here, the Boston dataset is a famous dataset which has Boston area house price and also some other variables, some demographic variables and some environmental variables. And there are the 14 variables and such as crime rate and the median house value. And each line represents one town. It may be just, I don't know exactly, but maybe the town or city or maybe zip code, but the certain area of the Boston suburb, that is each line. So in total, we have the 506 different towns in Boston suburb. So we have 506 observations. Okay, so yeah, so this is our console. So I think the dataset is in library mass. So you can type library mass, then Boston. So these are first 1, 2, 3, 4, 5, 6, 7, 8. So the first 6 observations of these 14 variables. And usually this median house value is the response variable, but here that we think about different variables. That is the distance from the city center and the NOx level, so chemical level. So at first, I make the scatter plot for these 2 variables. So the distance from the city center and the NOx, some harmful chemical level. So I think I have to attach the data set first, then this. Then you can see the nonlinear relationship between X and Y. And probably the first observation is probably that we want to transform NOx, for example, log scale. Also, you can see the distance is also skewed to the right. So a few observations on the right-hand side and many observations on the left-hand side. So it's skewed. So the natural instinct is to transform these variables, those 2 of the both variables by log. But actually, this still does not make the relationship linear. Maybe I can try that. So log of distance and the log of NOx. Yeah, we can see actually almost linear, but when we fit the linear regression, it doesn't work perfectly. So we just consider original scale, and we want to fit the spline on this. So this is the exercise 9A. So make a scatter plot. And okay, so we do we do fit spline, but we wanna split the data set into the training and the test. So at first, you can see the exercise sheet, and I set the seed, the random numbers, and then we split it into two data sets. So I use the sample function to randomly sample the 253 observations out of these 506 observations. So the half of the data will be training, and the half of the data set, the other half, are for the test. So the sample 101 to 506 and the 253. So, but it's more convenient to sort these numbers. So the sort, then it becomes increasing order. Increasing order. So this is basically the indices for training. Sample. Yes. So for example, head of IND, you can see the first observation and the 13 observation, 14 observation, 15, 16, and 19, and so on. So second to 12 observations are randomly assigned for the test. So training data set is this Boston data set, IND. Maybe to avoid confusion, maybe just the detach Boston, just in case. And then test set, maybe just minus the IND, then it's complement. Then training set, you can see the training set is the first line, 13th line, 14th line, 15th line, 16th line, 19th line, and so on. And the test set, you can see the 2, 3, 4, 5, 6, 7, and so on. So we have so we have now the test the training set and the test set. Actually, I have already sorted, so probably that we don't have to sort again the training set and the test set. Maybe the last two lines are redundant. Okay, so this is the part B. So now that we want to fit the spline. So the question C. So split the domain of distance into 4 intervals containing the same number of observations. So we have 253 observations in the training set. So approximately maybe 63 observations each. 63 times 4 is 252. So 53 to 54 observations. And so we set basically the 3 knots, right? So the 4 intervals, so 3 knots. And then we want to do the spline. We want to fit the spline. So for splitting the data, maybe you can use quantile function. For example, maybe you want to. This is just the example. If x is this, then the quantile of x at 0.3 is the 13.9, because the 0.3 means the 30% of observations are below this point. So these 3 observations are below this point, and actually the 13.9, and the other observations are above this point. So there are many definitions to define which value to take between 9 and 16. We have like 7 definitions in R, but we have some default value and we have something in between. Then the 30% of observations are below this and 70% above. Okay. Yeah, then using, this is C. Then D, they use the knot points. Sorry, they use these knot points that are defined in C, and the BS, the basis spline function, a basis function, to fit the regression spline to explain NOx by DIS. And then make a scatter plot of training set overlaid by the fitted spline, then evaluate the square root of the training RSS. or I think that training RSS. Maybe yeah, so usually we divide the RSS residual sum of squares by the number of observations, then take square root. So yeah, so maybe I have to say the divide the RSS by the number of squares, then yeah, then take square root. If it yeah. Then F, they make a scatter plot of the test dataset overlaid by the fitted spline. So evaluate the square root of the test RSS. Usually test RSS is larger. Then also we want to fit the smoothing spline to explain NOx by DIS. So smoothing spline, we have many knots. So if we have 253 observations in the training set, we have 252 knots. So observations, we have 253 observations, then we have 253 intervals, right? So with each interval, we take the knot. So then we can fit the spline. But we penalize the non-smooth curve so that the obtained curve is somewhat smooth. Then also you can optimize the the flexibility, so-called the effective degrees of freedom. So what's the optimal effective degrees of freedom? That you can test this by using some method, maybe cross-validation. Okay, so you can start the analysis. So I will split the group into several breakout rooms. Do you have any questions so far? Okay, so we have maybe 7 students, so maybe 2 rooms. And yeah. Okay, so maybe 10 minutes. Okay, so I don't know if you have enough time or not, but I will launch the poll. Okay. So actually, maybe the 4 of you have at least finished C, but C is quantile. Okay, so these D and E are spline. So actually, maybe 3 of you have finished E. So I will explain at least C, D, E, F or something. First, we split the data. Sorry. Okay, so quantile, we want to split the data into 4 equal intervals. So we put this and yeah, intervals. So probably we only need these 3 points. So maybe we define this as knots. So maybe KN or something like that. Oh. Quantile. Oh, okay, so we have to split this variable. No. Quantile. This is not found. So attach training set. So what's the name of the training set? This is TRN. Then KN is this. So these are points for splits. So you can see 2.1. So more observations here. So less than 2.1, the one group, and 2.1 to 3.36, maybe around here, one group, 3.36 to 5.2 around here, that is one group, and the larger than that, one group. So we want to split data into these 4 pieces and fit the spline. So we use the BS function. So BS distance. So we define this as BS. We have the 3 splits, 4 pieces. So BS4, I will say. The LM knocks on distance, but the basis spline of DS and knots is equal to KN. Yep. Error. BS is actually in the library. I think the splines library. So we have to fit it. So splines library. So library. So now that we have defined BS7, BS4. So BS4 is here. So you can see the basis spline function. So we have basically 4, 5, 6. How many pieces do you think it has? How many, variables in terms of linear model? You can see already. So we have the 7 variables here. So we have 7 of the 7 coefficients, right? So because the spline is basically the cubic function for each interval. So for the first interval, it's cubic function. So intercept, first degree, second degree, third degree. So we have 4 parameters. Then next piece, we have 4 parameters again. But because of the restrictions, it should be continuous from the first part, and the smooth and the second derivative coincide. So we subtract 3, so only 1 additional. So 4 plus 1 plus 1 plus 1. So we have 7 components. So we have 7 components and the 7 coefficients. So this is a BS4. And we want to see the fitted observations, so that we see we calculate the fitted value. So maybe BS4, training BS4. So predict BS4, and maybe just in case that we calculate standard error also. Then scatter plot again. So we only have training set, so we only take half of the observations, the entire observations data set. Then we overlay the line. So line distance training dot bs4 and fit the fitted value. Actually, the fitted function does not work, so $sign fit is needed. And then you can lines, the lines. Then we get this. Oh, I think we have trouble. Why? Because these 250 observations are in random order with respect to distance. So basically, we have all fitted 250 fitted value, but we randomly connect those 253 observations. So this happens. But we have to order observations in terms of DIS, distance. Then after that, you have to do that. So I think that we have to order this by increasing order. Yeah, sorry. So I think that we have to define. Yeah, so I think I stated something wrong. So we have to, I think the easiest way is that originally we order data by the size of distance. So TRN, training set is training set, but we change the order. So this is TRN, distance, and this, and all columns. So now the training data set is ordered by this distance, 1.13, 1.20, 1.28. So this is increasing order. Then we have to do this again. So maybe we attached the long data set. So maybe we detach again and attach again. Then we start over, sorry. So library already we attached, so that's fine. So BS4, we define this again, and the notes are the same. So that should be fine. So then predict. Then plot is the same, and then the lines. So now that it's ordered by distance, so we can see smooth curve. So we connect these 253 points in increasing order of distance. So we have the smooth curve. So we have here. So probably we don't have much difference in value. So we have some bump here, maybe influenced by this portion. So we have here, and up from 2.1 to 3.36, another curve. So this is a steep curve, and 3.36 to 5 point something. So we have, yeah, so curve with smaller slope. Then after that, the even smaller slope here. So that is the yes, piecewise cubic function, and this is the spline. Okay, so yeah, also you can add standard error. The standard error is also added by this lines function, so fitted minus standard error. And actually this TRN, the BS4 includes the standard error information. And the standard error also depends on the size of distance. So maybe just to see is much easier. So I just light it, draw it, lines, sorry, we have some mistake. Fitted value plus 2 standard deviations, so 2 times. So we get this. So you can see that at the center, the band is narrower because we have more information, but the both sides, basically, splines can blow up. The cubic function can blow up. So it has much wider standard error here and here. And minus 2 standard error, you can do in the same way here. So this is C. maybe only just CD. They make a scatter plot overlaid by fitted spline. So CDE, actually, CDE. But evaluate the square root of the training RSS in the, so evaluate the RSS. So we calculated the predicted value. So this fitted value and also actual, we want to compare. So actual value is NOx. So we take square, then take summation. This is RSS. So RSS, maybe training. So RSS.trn. And the summation of this. So this is 0.906. You can go back here again. So 0.9, yeah, so this is summation. So we have 253 observations. So average is this. Mean square error, MSE, 0.03. So you can see this is 0.1. So 0.03 is the 1/3 of this one interval. So that is the typical standard error size. Yeah, you can see, for example, this observation has much larger error. So 0.72 or something, and here 0.55. So the distance is 0.17, so much larger than this. Sorry, we have to take square root to make it more meaningful. So 0.06. 0.06 is basically the typical distance between the fitted line and observation. So as we have seen, distance maybe 0.1 or 0.2, but some observations are really close to the line. That is only maybe 0.1. So on average, in some sense, actually the square root of the average, squared average, that is 0.0598. So this is so-called RMSE, or root mean square error. So now, okay, so we detach R. Do you have any questions so far? So now we want to evaluate the test error. So this is training. So based on the observations, we make the curve, but we don't know if the curve fits well for the test data, especially, for example, this part, maybe, yeah, still many observations here. So we want to see it. So probably the test root mean square error is larger than training RMSE because we don't know the answer, basically. So attach TST, test dataset. Oh, test dataset also we have to transform it. So once we detach and then we attach again. Before that, we have to redefine it. So we order it by distance. So we want to do the same thing for test dataset. So test is ordered by distance. Then attach. Then test dataset BS4. So we want to only calculate the fitted value based on existing model BS4. So we use the BS4, but we have to replace data. So we have to specify the new data as TSD. So new data should have the same structure as old data. So we have used NOx and the distance. So we need those two columns in new data set with exactly the same name. Other columns may be different, but it should be the same name. The variable to be used should be the same name. So sometimes we feel that specifying the column number is more convenient than specifying the name of the variable. But here the benefit is the new data, they should have the same the variable names, but it can have the different the variable can be placed in the different columns. So that is a benefit to specify the name of the variables. Okay, so now the TST, so we calculate the fitted value. So it returns something, the warning message. So warning message isn't an error. So basically it's fine, but you have to be careful about interpretation or the result. So in BS something, the some X values the beyond boundary knots may cause ill the conditioned basis. So basically, okay, so we fit the lines, but maybe some observations are out of this range. They may be smaller than this value or larger than this value. That typically change the behavior of the observations. So maybe the fitted curve may not be good enough. But anyway, so it's not an error. So that should be fine. But at least you have to be careful about interpretation. So plot distance NOx. Yeah, you can see this observation more than 12, so it's larger. Here we don't really know, but actually more outliers here. Then lines distance TST dot BS4 dot fit. So we have the fitted line. It doesn't look bad. Probably if so this fitted curve is based on the training data set. So if we use this data set to fit the line, probably this place is, more flat curve, but here it jumps. Probably it captures only up to around here. So new data point here. So actually it blows up. Probably the last part is the third degree polynomial with the principal coefficient is positive. So like this. So it blows up a little bit. If we have the data point with distance equal to 18 or 20, probably it blows up. So it has a trouble. Yeah, so you can also put the dotted line, but that's basically the same as the last one. So I omit this, and we want to calculate the sum of squared distance. So last time we calculate this one, but we want to do this for new data set. So the test data set and the NOx we have now attached to the test set. So this should be fine. So RSSTSD. What's the value? 0.944. Last time this is 0.906. So it gets larger. That is natural because we don't know the answer. So the performance, the model fit should be slightly worse. And probably it's good enough. I think that these two numbers are pretty close. So it's good enough. To interpret this, maybe we divide this by the number of observations. Maybe some people claim that we should divide by this -7 because we have to subtract the degrees of freedom to make it unbiased. But here, just I use the simple number of observations here. Then here 0.0611. So the error size is slightly larger, maybe 2% larger than the training set, but that is natural. And this is actually the real, prediction performance. Yeah. And do you have any questions? If not, maybe G. G is the smoothing spline. So the question says, fit a smoothing spline to explain NOx by this. And what is the optimal degrees of freedom? So you can use the smooth spline function in splines package. So with the smoothing spline we have used what? We have used the 4 components. So degrees of freedom, effective degrees of freedom is 7, right? So we have 7 parameters. So I would name this as SS7, smoothing spline, smooth spline. Sorry, we want to now use the training data set. So the original sentence says, what, the fit the smoothing spline? Yeah, maybe the G is a little bit vague. So what data set to use? Maybe training set we use. So detach TST and attach TRN. Sometimes I detach twice just in case, but probably this is fine. TRN. sometimes you accidentally attach some data set twice. In such a case, you have to detach twice. So sometimes I detach until it returns an error. Okay, so attach to TRN and now smoothing spline. So SS7 as, okay, so I think that I named BS4, but maybe I should name it BS7. SS7 as the smooth spline. This is, okay, so X is equal to distance and the Y is equal to NOx, then DF is equal to 7. Yeah. Then now that we go to the smoothing spline, so I think actually the line function works on this object. So plot of yeah, so distance NOx, then we can overlay lines SS7. I think this is fine. Lines, this is just fine. So line here. I don't know how much difference it has compared to BS. Maybe I should say BS7, but I named it BS4 because it has 4 components. So lines BS4, maybe we change the color into 2, red color. BS4 probably does not work. Yeah, BS4 still that we have to, yeah, so do it as, you know, distance and the training BS4 fit. So you can see almost the same. Almost the same curve, but the slight difference, especially the left end. Also, maybe if you are careful, the right end. So you can see the red curve is component-wise cubic. So if we fit almost, just flat slope, then still we have to fit some cubic function. So like this. But the black one is very flexible. Just the it is imposed some penalty when it changes, you know, suddenly. So basically, it is a smooth curve. It's not any, you know, straight line, or it's not the cubic curve or something, but the entirely it's smooth over the entire period. So basically, the flexibility of these two curves are the same, but it behaves slightly differently. Which one you should think better? You know, it's hard to decide, but it looks smoothing spline is more natural for me because we have this bump. Maybe it's affected by this one, but it's pretty unnatural to assume each component is cubic. So black line, maybe more natural. Yeah, and finally, okay, so we want to find the optimal, the degrees of freedom, the effective degrees of freedom for smoothing spline. So SS optimal by cross validation. So we don't specify DF, but we set the CB option as true. Then optimal smoothing spline with optimal degrees of freedom. So it returns some warning message in smooth spline cross validation with non-unique X values seems doubtful. Sorry, I don't exactly sure about the reason, but maybe it is because the original distance data has some ties that may make some trouble. Yeah, but for now we ignore it and we see that what's the result, SSCB. And you can see that the degrees of freedom 5 is optimal. So actually the 4 components, I mean, DF7 is maybe too much. So even simpler curve is better. And leave one out, cross validation 0.0037. This is probably original scale. So we have to take square root to get the cross validated error. RSS was originally what this is test RSS, so 0.9449. So this is the basically test error, and the CV error is kind of similar to test error. So 0.916 is smaller than that, so probably it's a more optimal one. So lines SS CV, we also plot this maybe color 3. Then this is optimal line. So actually it doesn't change much. The green line and the black line are almost the same. Maybe black line fluctuate here and fluctuate around here, but it's not necessary. That is the answer. So anyway, it sounds the difference is small. Okay, so that's it. So do you have any questions? Yeah, so I got some questions during breakout sessions about the final project data. So I shared something. I think that Paula asked me about the psychology data, and I'm not sure, but when I Googled it, then we have some links to the data, so maybe that may be useful. And also I uploaded the Stat 5030, the data source guide to the Canvas website, so you can see what the data are available. So generally, governmental organizations or some institutions for each area of the study, or such as maybe sports or finance, that may be useful. International organizations also has data, the UN, OECD, and so on. So generally, it's harder to find the data for 5820 compared to 5030. 5030, it's simpler projects, so simpler data are fine. But 5820, probably you want to get more complicated data, so that's why I don't deduct any points when you use the data repository data. So you can also use UCI or data.cov, those data. Okay. Any questions so far? If not, I go to chapter 8. At least it's maybe useful, beneficial to discuss part of chapter 8, maybe to brainstorm the final project if you haven't. So chapter 8. Sorry. Have you decided the data sets for the final projects?
I think so.
Oh, okay, good. I have already one submission. I have already seen one submission, but you have a couple of days still. Okay, so now chapter 8. So today I want to discuss the theory and the ideas. So tree-based methods. So idea is here. So this is basically the baseball data, I think, and the professional baseball player's salary, how it is determined. And this is the application of tree method. So at first, the salary is different for players with less than 4.5 years of experience and more than 4.5 years of experience. That makes some sense, right? So that is the biggest difference. And if the experience is longer, then the number of hits in the last season is most important factor to separate the cases. So if number of hits is less than 117.5, that means 117 or less, then the salary is 6. This is like the log of something. So log of salary is salary in $1,000 or something. So 6.0. But if more than that, then the average salary is 6.74. So we split the cases, and for each case that we consider the salary. So that is the regression tree. So it's very intuitive, right? So the years of experience is most important, and the number of hits. And maybe after that, we may have the same variables. For example, number of hits is more than 117.5. Then we further split it into two categories, like the players less than 20 years of experience and more than 20 years of experience. And maybe less than 20 years of experience, maybe salary is higher or something like that. So we split in this way. So this is regression tree. So this is the graphical image. So these are observations, and that we split up first here, then second here. Then we have 3 regions. And we fit the constant for each region. That is the most common application, but possibly we can fit the more complicated, function for each region. For example, the linear function of hits and the years and intercept. Yep, that is another possible way. And we divide here, divide here, divide here, and how many times we divide? Okay, so anyway, we optimize the number of splits later, but we can divide until each region has smaller than a certain number of observations. For example, suppose that we have 200 observations, then we split until each region has at most 5 observations, for example. And this is more complicated case. So probably we split the data set into this pink part and the light blue part first. Then next step is, I don't know, maybe this maybe light blue and thick light blue, we split here, or maybe other place. And maybe third one is the by x2 and split this slightly thicker pink and the slightly brighter pink. So here and here. And finally, maybe we split this by x2, but of course this is different x2 value here and here and here. It seems the colors are the same. So we have the 4 splits, and we have basically 5 cases. So this is the regression, one example of regression tree with 2 variables. So sometimes we split the data by x1, sometimes by x2. Yeah. And okay, so first we make a big tree. So we split until each region has less than 5 observations. Then after that, how to determine optimal T? We have to stop in the middle because the large tree is too complicated rule. So that we minimize this value, objective function, to optimize the tree. And here, yi minus y hat. So this is basically, the squared error. So squared residuals. And the squared residual is the basic thing for regression, but also we penalize the size of tree. So this is the size of tree. So if the size of tree means in the previous case, we have the 5 stages, so 5 cases, so T is 5. And the alpha times 5, alpha is a given constant. Alpha times T is penalized. So in this way, we want to minimize this. In this way that we can optimize the size of tree. So what happens if alpha is infinitely large? So if alpha is large, then penalty is large. So probably the tree size is 1. So just a constant for all observations. What happens if alpha is 0? Alpha is 0, then no penalty. So larger tree is better because we separate more cases. So the size of tree that blows up. So small alpha, less penalty. So larger tree. Large alpha, the tree gets smaller. And somewhere in between, we should have an optimal alpha. Yeah. And yeah, so first we made a big tree, right? So we have the tree until each, separated cases have less than 5 observations. And after that, based on alpha, we have optimal, the tree size T. So to be exact, actually the trimming is different from original branches. So sometimes we combine the two nodes in a different order. Yeah, maybe I explained that. So sorry, I think this is an old version, but anyway, so sorry, so just a minute. Yeah, so this, yeah, so it's possible that for example, that we have x1 and x2, like x1, x2, and that we have here, maybe just for simplicity, this is the classification data, and we have, for example, maybe 4 clauses around here and 5 circles around here, and there's 4 clauses around here, and maybe 1, 2, 3, 4 circles, maybe 3 circles, and 10 clauses around here, 5, 6, 7, 9, 10. Then maybe the first split is here. Maybe left-hand side, more circles, right-hand side, less circles. Then after that, maybe, yeah, maybe we put maybe 2 of the, maybe after that, maybe we put here, maybe the more circles above this and the less circles below this. Then after that, maybe that we split the case. Sorry. I think this is too complicated situation. So maybe I just make a simpler example of just x1. We have maybe one category here and another category here. Category 0, category 1. Sorry, this doesn't work, sorry. It's pretty complicated. So the x1, x2, Yeah. Mm. Sorry. Sorry, I cannot really make a good example, but suppose that we have something like that, then okay, so more circles on the right hand side. So maybe the first split is here, second split is maybe, sorry, then maybe we slightly have more clauses here. Oh. So more circles on the right hand side. So maybe first split is here, and the second split maybe, you know, maybe here, because the below more circles. Then the fourth split maybe here, and the fifth split maybe here. So the third and the fourth here. And but after we split this and this, actually these pairs are really good splits. So at first it does not look good because the, you know, the above and below, the both we have crosses. But after we also separated here, then actually it looks much better. So in such a case, maybe this one and this one are the last ones, but maybe we keep this one and also this one, and we prune this, you know, the split. We vanish this split. That may be also possible. So if we split the tree into several pieces, then we, you know, cancel the split later, but the order of cancellation may not be exactly the same as original construction of the tree. Yeah, then how to determine alpha? So alpha is a hyperparameter. It's similar to the lambda in rich regression. So remember that the RSS plus lambda times the size of the coefficient vector beta is the rule, the objective function in the rich regression. And the lasso case that we have the L1 penalty here. So this lambda and this alpha are similar parameter. So generally, hyperparameter should be optimized by cross-validation. So how to do that? So basically, for each value of alpha, at first minimize the objective function to determine the optimal subtree. So subtree is obtained by removing some of the splits in the original tree and making a subtree called pruning. Okay, so for each alpha, we make a tree. Then we compare these trees by cross-validation. And by doing that, we can optimize alpha. So alpha is large. We have more penalty, so smaller tree. So alpha is small, larger tree. But anyway, the tree size is finite. So we don't really have to try all possible values of alpha. Suppose the largest tree has only, 30, the size of the tree is only 30. Then if we make alpha larger, tree gets smaller. And at most, we have to try the 30 cases. So we have to try 30 alphas corresponding to each size of tree. So then we optimize alpha by minimizing cross-validated error. So this is the summary of the regression tree. So at first, they make the largest tree based on the method in slides number 3. So we split until each node has less than certain number of observations. Then after that, for each alpha, we prune the original tree to minimize the cost function in the slides number 5, previous page. Then use cross-validation to find the optimal alpha and adapt the subtree obtained by the optimal alpha in this step 2. Anyway, it will be done in the computer algorithm. But do you see the idea? Okay, so in the previous page, it was the regression tree because we minimized the residual sum of squares, but also it can be applied for classification trees. So tree method can apply for classification problem in the same way as the regression tree, with the different error functions to be minimized. Two most popular functions for binary classification problems are as follows. So one is deviance and the other is error rate. So deviance is basically the maximum likelihood. So log of maximized likelihood. So that is the value. So this is the likelihood function. So suppose that we have the, okay, so for each node, we have the number of observation that is ni, and the lowercase n of I successful cases, and the ni minus lowercase ni failure. Then the likelihood function is the success probability for that class to the power ni times 1 minus pi to the power ni minus ni. Right? But the ni is actually capital Ni times pi, right? No, capital Ni times pi, I believe. And times 1 minus pi times n times 1 minus pi. So if we take logarithm, then that becomes this. So log likelihood function is, yeah, so log likelihood function becomes this, but negative 2 times log likelihood function. So we minimize this function to get the optimal tree. And another one is error rate. So error rate is just a proportion of observations classified incorrectly. So what are the differences in real examples? What happens when we use deviance and what happens when we use error rate? Deviance has basically more information because it's likelihood function. So it's optimal in some sense, statistical sense. On the other hand, it is not robust against outliers. So if we have outliers, then error rate is more, stable. But the error rate just only, the 0, 1 for each observation. So correct or incorrect. So it has less information. So error rate, maybe the benefit is robust. It's robust. And this one, maybe more information. Statistically more optimal. So these are the differences. So I think the deviance is usually better because classification problem, we don't have enough information. So deviance works better, but if we have outliers, maybe it's different. Okay, so it's already the 6:48. Yeah, just maybe I finished the 2 slides. So what's the real performance of tree-based method and linear methods? And it really depends on the problem. So if the truth is this, so we have the 2 predictor x1 and x2, and this is the region for class 1 and the region for class 2. And if truth is this, of course, the linear boundary works better. If we use the class 3 method, that we have to have this complicated the classification method. So linear case, and the 3. And this is much better. But if true boundary is like this, then certainly this one works better. So it depends on the truth, which is better, linear or tree methods. And the advantage of the tree method is at first very intuitive and displayed graphically. So we split the cases by the year of experience to determine salary. It's very intuitive for human. And also, another benefit is no need to create dummy variables for categorical predictors. So you can see categorical predictors is complicated. If we have 5 categories, we basically prepare the 4 dummy variables, and we see the difference between the base level and another variable. But for this one, basically this is the user side advantage. But basically tree method consider all combinations of splits. If we have the factor variable with 5 classes, C1, C2, C3, C4, C5, we split the algorithm, split this into 2 classes like C1, C3, and C5, and C2 and C4, or some other splits. Then it choose the best splits. So in that way, at least it looks simple. So we don't really have to prepare all dummy variables. And the disadvantage is prediction performance is generally not high unless we use some more advanced improvement methods. And not robust, the split, it really depends on the data, right? So if we have only the X1 as a predictor and so this variable, then, maybe split at here. This is one good way, but also split at here is a good way, right? So maybe I would say that if we have one more failure here, then split is here. If one observation here, then split is here. But if it does not exist and we have one more observation here, then split is here. So only slight difference in data get dramatically different, the results, so not robust. And this is also hard to interpret, but the methods often suffer from overfitting. If we do some cross-validation and make a very good model, then after that we import the test data, then it does not fit well. So that is the thing, it can happen. So it's a kind of mysterious, but sometimes the cross-validation, even cross-validation is not enough to evaluate the performance and often suffer from overfitting. So that's the regression trees. And later sections that we improve these tree methods. So original ideas are the same, but the algorithms are improved so that the prediction performance is better. Okay, so do you have any questions? If not, that's it for today. So project plan is due on April 1st. So just submit your plan. Okay. Okay, so see you on Thursday.